Welcome back to Arkaan channel. In the video this time I am not the material carrier, but this time the one who will bring the material is the creator of this channel and his 4 friends. The material in question is electrostatics, charges and fields. Before that, don't forget to like, comment, share this video and also subscribe to this channel so that this channel will be active in the future. Enjoy this video.
Assalamu'alaikum warahmatullahi wabarakatuh. Hello guys, my name is Muhammad Arkaan.
My name is Indri Armin.
My name is Fira Alfiani.
My name is Muhammad Abdi.
My name is Fira.
We are from Group 1. We will bring you a material on electromagnetic charge and fields. The electric force between two charges is given by Coulomb's law. A very useful concept is the electric field, which is defined as the force per unit charge. Every point in space has a unique electric field associated with it. We can define the flux of the electric field through a given surface. This leads us to Gauss's law, which is an alternative way of stating Coulomb's law. In cases involving self-Fission symmetry, it is much quicker to calculate the electric field via Gauss's law than via Coulomb's law and direct integration. Two facts help to explain the continuing importance in modern physics of the classical description of electromagnetism. First, special relativity requires no revision of classical electromagnetism. Historically speaking, special relativity grew out of classical electromagnetic theory and experiments inspired by it. Second, quantum modification of the electromagnetic force have turned out to be unimportant down to distance less than 10 to the power of -12 meters, 100 times smaller than the atom. Certainly, one fundamental property of electric charge is its existence in the two varieties that were long ago named positive and negative. If two small electrically charged bodies A and B, some distance apart, attract one another, and if A attracts some third electrified body C, then we always find that B repels C. The total charge in an isolated system never changes. By isolated, we mean that no matter is allowed to cross the boundary of the system. Within the system, charged particles may vanish or reappear, but they always do so in pairs of equal and opposite charge. The charge conservation law. The total electric charge in an isolated system, that is, the algebraic sum of the positive and negative charge present at any time, never changes. This law meets the test of relativistic inference. The answer is that it does, and not merely in the sense that the statement above holds in any given inertial frame, but in the stranger sense that observers in different frames, measuring the charge, obtain the same number. In other words, the total electric charge of an isolated system is a relativistically infinite number. In our study of electricity and magnetism, we shall treat the charged particle simply as carriers of charge, with dimensions so small that their extension and structure is, for most purposes, quite insignificant. Rutherford's analysis of the scattering of alpha particles showed that even heavy nuclei have their electric charge distributed over a region smaller than 10 to the power of -13 meter.
As you probably know, the interaction between stationary electric charges is described by Coulomb's law. Two stationary electric charges repel or attract each other with a force that is proportional to the product of the magnitude of the charge and inversely proportional to the square of the distance between them. With this equation, here Q1 and Q2 are numbers indicating the magnitude and charge sig respectively. R vector 21 is a vector unit in the direction from chair 1 to chair 2, and F2 is the force acting on chair 2. Equation refers the fact that the force obeys Newton's third law, that is, F2 equals mean F1. In principle, Coulomb's law is part of electrostatic. Given their chair and location, we can find out the electric force, or given that the charge is free to move under the influence of other force as well, we can find an equilibrium arrangement in which the distribution of the charge remains at rest. In the same sense, all Newton's law motion applies to mechanics. The force that must be applied to move one chair to other is equal and opposite to the Coulomb force with this equation. This material has important application in crystal physics. We know that an ionic crystal such as sodium chloride can be described in a very good way as an alternating arrangement of positive ions and negative ions in an ordinary three-dimensional arrangement or lattice. In sodium chloride, the arrangement is shown in the following image. Of course, the ions are not point charge, but they are an almost spherical distribution of charge, and therefore, the electrical force they exert on each other or the same is each the ion is replaced by an equivalent point charge at its center.
The electric field is merely another way of describing the system of charge. It does so by giving the force per unit charge in magnitude and direction that an exploring charge K0 would experience at any point. We have to be a little careful with that interpretation. Unless the short charges are really immovable, the introduction of some finite charge K0 may cause the short charge to shift their position so that the field itself. Maybe you still want to ask, what is an electric field? The electric field is attached to every point in the local property system. In this sense, if we knew E in some small neighborhood, we knew without further inquiry what would happen to any charge in that neighborhood. We don't have to ask what the field does. We can show the size and direction of E at various points by drawing small arrows near those points, making the arrows longer where E is larger. Volume load distribution is described by the scalar load density function ρ, which is a position function with a charger or volume dimension. That is, ρ volume element give the amount of content contained in the volume element. If the power field charge become a continuous charge distribution rather than the main charge, we can change the amount in equation 1.20 with the appropriate integrals. Integrals provide an electric field on x, y, and z, which is produced by charge at other points x-axis, y-axis, and z-axis. We must emphasize that our definition of log applies to any vector function, whatever physical variable it may represent. Now let's add flux through all the fillings to get the flux through the entire surface. The number of scalar that we will describe with this equation.
The flux of the electric field E through enclosed surface, that is the integral E dA over the surface, equals 1 per epsilon 0 times the total charge enclosed by the surface. Look at these equations. For Gauss' law, we call the statement a law because it is equivalent to Coulomb's law and it could serve equally well as the basic law of electrostatic interactions after charge and field have been defined. Gauss' law and Coulomb's law are not two independent physical laws, but the same law expressed in different ways. In Gaussian units, the 1 per epsilon 0 in Gauss' law is replaced with 4p. The picture about the electric field of a spherical charge distribution. Because of the spherical symmetry, the electric field at any point must be radially directed. No other direction is unique. Likewise, the field magnitude E must be the same at all points on a spherical surface as 1 of radius R1, for all such points are equivalent. Call this field magnitude E1. The flux through this surface S1 is therefore simply 12p R1 square E1, and by Gauss' law, this must be equal to 1 per epsilon 0 times the charge enclosed by the surface. Or, look at this equation. Gauss' law leads directly to the same result. Surround a segment of the line charge with a closed circular cylinder of length L and radius R as in picture, and consider the flux through this surface. As we have already noted, symmetry guarantees that the field is radial, so the flux through the ends of the thing is zero. The flux through the cylindrical surface is simply the area 2PRL times ER, the field at the surface. On the other hand, the charge enclosed by the surface is just lambda L. So, Gauss' law gives us 2PRL ER equals lambda L per epsilon 0.
Electric charge distributes smoothly in a thin sheet. It's called surface charge distribution. The outward flux is found only at the ends, so that if EP denotes the magnitude of the field at P and EP exen the magnitude at P exen, the outward flux is A EP plus A EP exen equals to 2 A EP. The charge enclosed is sigma A, so Gauss' law gives 2 A EP equals to sigma A per epsilon 0, or belong to this equation. Next, we're gonna talk about the force on a layer of charge. Based on this picture, Coulomb repulsion between charge within the patch is just another example of Newton's third law. The patch as a wall cannot pass on itself, the simplest of our problem, for it allows us to use the entire electric field E, including the field due to all charge in the patch, in calculating of force dF on the patch of charge dQ. dF equals to E dQ equals to E sigma dA. Next is energy associated with the electric field. Suppose our spherical shell of charge is composed slightly from an initial radius of R0 to a smaller radius. This requires that work be done against the repulsive force, which we found above to be sigma square per 2 epsilon 0 Newton for each square meter of surface.
Enough of the video this time, hopefully useful. See you in the next video.